we saw our first pictures from Viking of the dissected tableland, we saw the deeply incised stream channels, and we finally gotten some measurements of what the gradient of those streams is, and it runs between 10 and 20 meters per kilometer, which is a very steep mountain stream type of gradient. And sure enough, we have mountain-looking streams. They're very large ones, and we decided we had to get beyond this dissected tableland area and beyond the area of knobs that we thought would extend northward. So we laid down our photo strips, and we had hoped that in like three photo strips we'd be well beyond the edge of the dissected plateau and run out of knobs. And sure enough, last night, as those pictures came in, we had left all of those other hazards behind, and we were out in the cratered plains that lie north of the area we had been looking at earlier. It's between 2 and 3 kilometers below our zero Mars level, so we're in a very low, very smooth area. We've left behind all the other kinds of hazards that we saw in the A1 site, and the only thing we have left is cratering. And there's a line of craters on the south and a line of craters on the north, so choosing an ellipse position we think is going to be very easy. It also happens that the Arecibo radar trace runs right down the middle of that smooth area. So we hope that it'll come back loud and clear, and that all of our data sources will agree that this is the best chance that we have of landing safely in this area. We ran through a number of calculations about first the crater flux in this area versus the A1 site that we had looked at before. And the crater curves lie significantly down. So the number of craters in the unit area are much smaller in the site that we've chosen. We've looked at the probability of landing on other kinds of features. In the nominal A1 site, the numbers were running like 9, 10, 11% chance of landing on hazards other than craters. We did the computations for our new site, and they run like 1.5 to 2.5. So we think that on all counts, both from craters and other kinds of things, the indications were very clear and very straightforward, and everyone enthusiastically adopted our Northwest Territory. There are two fascinating things that have come out of the multiprobes that went down through the atmosphere of our Pioneer Venus and the Soviet spacecraft, and the orbiter, because both have made measurements of the clouds and the composition of the high atmosphere. First, they confirm that the clouds are made of sulfuric acid. That's a very strong acid, and little tiny particles form the cloud deck. Second, and even more interesting, is the composition of the noble gases. We've analyzed for argon, xenon, krypton, those components that we thought we understood very well, and we think they're derived from the original composition of the atmosphere plus their generation by the radioactive materials in the crust of the planet. So they're very important indicators of how far the planet has evolved. When we go from near the sun to farther out, we're supposed to have more volatiles. More volatiles means more noble gases. So going from Venus to the Earth to Mars, the composition of the noble gases should go up. Unfortunately, it's exactly the opposite. There's almost 100 times as much noble gas in the Venus atmosphere as in the Earth, and again 100 times as much as in the Mars atmosphere. So the trends are exactly opposite to what they should have been from the predictions.
Yes, looking at the back side of it, I guess we're looking almost right down the long length of it toward Jupiter. But there is a little bit of piece of structure around the edges there. I wonder if you had any chance to look at that at all yet.
Yes, only very, very briefly. It reminds you a little bit of the groove terrain that we saw on Phobos, the satellite of Mars. Mm-hmm. When we got high enough resolution pictures, this what looked like a very simple, straightforward impact cratered object had this very complex patterns and things that some people are attributing to all being radiating fractures from impact craters. Other people say, well, they have raised rims and something had to come out of those holes. Yes, there was an impact, but you also had some internal activity. since it's such a tiny body, both of these are very small, then it's really hard to make a good story. One of the suggestion was that you flex it a little bit by tidal forces, the same kind of thing that makes eel active, and you heat it up just enough to get just a tiny bit of internal activity. So it's almost, let's say it's 99.9% impact, but maybe a little tiny contribution of some internal activity.
Well, speaking of holding your breath, we've been doing it for about 3 years, sure that these satellites were going to be fascinating. And we finally got some pictures last night and this morning that show that they are at least as fascinating as we hoped they would be. This is an early, very bad picture, but maybe you can see a nice round feature here with what looks like a central peak. And in this one, you can see lots of closed, what look like closed depressions.
Yes.
Now, I'm almost sure that's a real, honest-to-God impact crater of classical shape. And we have a violent argument as to how many craters you can see in this view now. And I think we have a triple margarita bet as to whether there are 3 or 25 craters.
That's quite a difference. Suppose there's 17. Who wins?
We'll probably each drink a third of it.
And it has quite rectilinear, angular, bright and dark things. And here we can see beautiful faults that bound those, and another fault that cuts across these. And then finally, tracing that fault off into the distance, here's the chevron again, and the small faults go off, and here we see an enormous fault scarp that we've measured.
That's a cliff.
That's a cliff that is probably at least 5 kilometers high. We don't have a very good number on it yet, but that has some striations on it. And that might mean the faulting has polished that and grooved that surface. So we know the sense of movement, and we see the topography offset. Now we have to put all of these ideas into something that fits together. And here's where our either working prejudice or our multiple working hypotheses come in. And we've had a very interesting discussion this afternoon with, of course, universal agreement instantly on everyone's part.
I can imagine how much agreement there's been on everyone's part. Well, it's a baffling set of pictures.
Well, what really is interesting is you try to work on, say, an impact origin for all of them, and you fill stuff in. You have stacked layers. That was one of the early ideas coming in, that it's a volcanic thing with layers coming this way, that it's a great hunk that's been buried and is now re-exposed in the crust. But the fascinating thing is to say, take that idea and pursue it. Test it against the crater counts, the way the faults are, early, late, does it make sense? And that's where the real fun in our game comes in. The exciting part is planning it, carrying it out, getting the pictures down on the ground. Then the real battle starts of geologic ideas.
Wouldn't it be excellent if you could actually get out there and walk around on the surface, collect a few samples?
Yes.
Right. This is the real challenge. They have to do it this way.
Yes, but you get very cold feet.
Thank you, Hal.
Each time we've flown by a new planet with its satellite systems, we've been enormously surprised because each of the groups are different, and within the groups there are differences. It's like having a family with a lot of cousins, and the cousins are similar but distinct. And then you go to another family group, and they're again similar but different. The whole group is different from the previous one. So it's been a very exciting voyage.
It certainly has.
Well, each time you see things at higher resolution, it radically changes your idea.
Sure.
If you see a bright or a dark streak, somebody will say, it's a wind streak. It's a fumarole, that is, with material spewing out from underneath the surface and blowing downwind. And some people say those are hills, and all the shadows are pointing in the same direction. I prefer saying they're dark streaks and not call them wind streaks, because pretty soon you begin believing that yourself, and you forgot that you just made up that idea an hour before.
You want to make sure you don't prejudice yourself, right?
It's the philosophic way of approaching it is so-called multiple working hypotheses rather than single working prejudice. And it's very easy to hypnotize yourself. You know, it becomes your child. So you have to defend it even though you have to distort the later data incredibly to make it fit your earlier conception.
Right, which is the wrong way.
And that's the wrong way to do things. Don't dig a pit. It's too easy to fall into it.